Welcome, curious minds, to another deep dive. Today, we're really digging into something fundamental in artificial intelligence. How do these incredibly smart systems, the ones recognizing faces, driving cars, even beating us at chess, how do they actually think? How do they solve problems? Because underneath all that complexity, it often boils down to one core idea: search.
That's exactly right. And our mission today is really to, well, cut through some of that complexity, give you a kind of shortcut to understanding how AI sifts through, vast numbers of possibilities to actually find a solution. We've got a bunch of insights, analogies, trying to unpack the key ideas, the techniques, the algorithms behind AI search. And it's fascinating because it's not just about computers, is it? It's about problem solving itself, but formalized so a machine can handle it.
Yeah, it's easy to think search is just like typing into Google. But in AI, it's way deeper than that. Think about Google Maps figuring out the best route, like instantly.
Yeah.
Or an AI playing chess, making that killer move. How does it do that? It starts by seeing the challenge as a search problem. Okay, let's unpack this. So to start off, how does an AI even frame a problem? What are the absolute basics it needs before it can even try to think about solving something?
That's a really good place to start because it all begins with formalizing it, putting it into boxes the computer understands. First, you need the agent. That's the thing doing the work. The problem solver could be your maze-solving program or maybe an AI managing cloud servers. And there's the environment. That's just the world the agent lives in, the maze grid itself, or, the whole network of virtual machines.
Okay, the agent and where it operates. And I guess you need to know where the agent is, right?
Precisely. That's the state. A specific snapshot of the agent and environment at one moment. For a self-driving car, it's like its exact location, speed, other cars around it, all that stuff. For maybe a logistics AI, it's the current stock levels, truck locations.
And the initial state is just where it all begins, the starting line.
Exactly, the clean slate. Now, to get from one state to another, the agent has actions. These are the choices it can make. Turn left, allocate this resource, move that chess piece. And the rules of the game, basically that's the transition model, sometimes called the result function. It tells you if you're in this state and you take this action, you end up in that new state. It's the physics of that mini world.
Okay, so you have where you are, what you can do, and what happens when you do it. And if you mapped out every single place you could possibly get to, what's that called?
That whole map, all the possible configurations reachable from the start, that's the state space. Think of it like this enormous, incredibly complex roadmap. Every possible situation is an intersection, and every action is a road connecting them. And this is key by formalizing problems this way. Even really messy real-world stuff becomes a structured map, something a machine can navigate even though it doesn't see the world like we do.
Right, it turns into a puzzle it can actually work with.
Exactly. And it needs to know when it's done, right? That's the goal test. Did the robot grab the package? Is it checkmate? Is the server optimized? And finally, the path cost. This puts a number on a sequence of actions. Could be time, money, energy, or just, how many steps it took. Often, the AI isn't just looking for a solution. It wants the optimal solution, the cheapest, fastest, shortest path to that goal.
Okay, so we got the map, the start, the finish line, the costs, the whole setup. But then how did the AI actually navigate this potentially huge, bewildering state space? Does it just wander around?
No, not randomly. It's actually quite systematic, usually. It uses a few core tools. When it explores, it creates these things called nodes. Think of a node like a little digital index card for each state it considers. It remembers the state itself, how it got there, its parent node, the action taken, and the total cost so far to reach that point.
Okay, like breadcrumbs it leaves for itself.
Sort of, yeah. And it keeps track of where it could go next on something called the frontier. That's its to-do list of nodes to explore. And crucially, it also keeps a list of places it's already finished exploring. The explored set. This is super important to stop it going in circles. A to B, B to A to B forever.
The been there, done that list. Makes sense.
Right. So the general process is this loop. First, check the frontier. Is it empty? If yes, well, no solution found. Give up. It's not empty. Pick a node from the frontier. How it picks is key, but we'll get to that. Is this node the goal? If yes, fantastic. Trace back through the parent pointers and the nodes to get the path. If it's not the goal, add this node to the explored set market as done. Then you expand the node.
Expand. What does that mean?
It means you look at all its immediate neighbors, all the states you can reach directly from the current one using just one action. And then for each neighbor, if you haven't already explored it and it's not already waiting in the frontier, you add it to the frontier. Then the loop repeats. pick another node, check if goal, explore, expand. And the absolutely critical thing here, the thing that defines the whole search strategy, is how you choose which node to pull from the frontier next.
So the picking strategy is everything.
It determines the whole character of the search. And yeah, the data structure you use for that frontier, like, is it a stack, a queue, something else that defines the strategy? And this leads us straight into our first big categories of search, the uninformed ones.
Uninformed search.
Okay.
What does that mean? Is it like searching with the lights off?
Pretty much. Or maybe navigating without a map or compass. These algorithms don't use any extra clues about how close they might be to the goal. They just follow the rules. First up, we have depth-first search, DFS. Its strategy is simple. Go deep, pick a path, and follow it as far as possible. It uses a stack for its frontier last in, first out. Like a stack of plates, you always take the top one off, so it always expands the deepest node it hasn't finished exploring yet. If it hits a dead end, it backtracks just enough to try the next available turn and dives deep again.
Okay, relentless pursuit down one corridor at a time. Does it always find the goal?
If the maze, the state space, is finite and a solution exists, yes, DFS is complete. But, and this is a big but, it's not necessarily optimal because it commits so hard to one path, it might find a really long, winding solution even if a super short one was nearby.
Right, it might go all the way around the block when the door was right there.
Exactly. The upside. Sometimes it can be quite memory efficient. Because it's only really exploring one path deeply at a time, it doesn't necessarily need to remember a huge number of alternative options simultaneously.
Okay, so DFS is deep, maybe not shortest, but potentially saves memory. What's the alternative?
The main alternative in uninformed search is breadth-first search, or BFS. BFS does the opposite. Instead of going deep, it explores layer by layer. It uses a queue for its frontier, first in, first out. Like a line at the checkout, first one in is the first one served. So it explores all the nodes one step away from the start, then all the nodes two steps away, then three, outwards in concentric circles, kind of.
Like ripples in a pond. Okay, I can picture that. What are the pros and cons there?
Well, like DFS, it's also complete in finite spaces. If there's a solution, BFS will find it. And here's its big advantage. BFS is optimal, but only if all the steps, all the actions have the same cost, like in a simple maze where each step is just one unit. Because it explores layer by layer, the first time it reaches the goal, it must have found the path with the fewest steps. Guaranteed.
So BFS gets you the shortest path if steps are equal cost? That sounds great. What's the catch?
The catch is memory. Because it explores so broadly, keeping track of all nodes at the current depth, the frontier can get huge. Especially if the goal is far away, BFS can be very memory intensive. It might need to store a massive number of states.
Okay, so BFS, shortest path for equal costs, but a potential memory hog. DFS might save memory, but could take you on a wild goose chase. Feels like a bit of a trade-off. Is there a smarter way? Can we give the AI some hints?
Absolutely. And that's exactly where informed search comes in. We move beyond just blindly following paths. Informed search algorithms use problem-specific knowledge, extra information to guide the search more efficiently. This extra knowledge comes in the form of heuristics.
Heuristics. Okay, that sounds fancy. Is it just a guess? How does that work?
It is basically an educated guess, a rule of thumb, a gut feeling, if you like, about how close the state is to the goal. It's an estimate, crucially, not a guaranteed perfect measure. We formalize this with a heuristic function, usually written as HHN. It takes a state n and returns a number estimating the cost from that state to the goal. A really common example, especially for grid-like problems like mazes, is Manhattan distance.
Manhattan distance, like city blocks.
Exactly. You just count the number of steps horizontally and vertically to get from where you are to the goal, ignoring any walls or obstacles in the way. It's obviously not the real path distance, but it's a quick, cheap estimate, and often it's a pretty decent hint.
Okay, so we have this estimating function, HAHN. How do algorithms use it?
Well, one simple way is greedy best first search, or GBFS. Its strategy is, well, greedy. It always chooses to expand the node that looks closest to the goal based only on the heuristic value, HHN. It ignores how far it actually traveled to get there. It just goes for whatever seems like the quickest win right now.
Sounds direct. Is it any good?
It can be very fast in terms of exploring fewer states if the heuristic is good. It makes a beeline for the goal. But because it's greedy and only looks at the estimated future cost, it's not optimal. It can easily be fooled. It might take a path that looks great initially but leads into a really long detour or a dead end, when a slightly less appealing first step might have led to a much better overall solution.
The classic Short-term gain, long-term pain problem. Okay, so greedy isn't the answer for optimality. What is?
The gold standard, really, for optimal informed search is A search, often just called A star. A is smarter because it balances two things. It looks at the estimated cost to the goal, that's our heuristic, HN, but it also considers the actual cost already spent to reach the current node from the start. We call that GN. A always chooses to expand the node with the lowest value of GN plus HN, the sum of costs so far plus estimated cost remaining.
Okay, that makes intuitive sense. It's like balancing how far you've come with how far you think you still have to go.
Precisely. It's weighing the past investment against a future prospect. Now, A is incredibly powerful and it is optimal, but with some important conditions. First, the heuristic function, HNM, needs to be admissible. This is critical.
Admissible. What does that mean?
It means the heuristic must never overestimate the true cost to reach the goal. It can be pessimistic, estimate higher than reality, or perfectly accurate, but it can't be overly optimistic. If it thinks the goal is closer than it really is, it might mistakenly prune away the actual optimal path. Second, ideally the heuristic should also be consistent. This is a bit more technical, but basically means the estimate should behave logically as you move between adjacent states.
Okay, so if your heuristic is well behaved, never overestimates,
Yeah.
and is consistent, A will find the cheapest path.
Yes. And it will generally do so much more efficiently than uninformed methods like BFS because the heuristic guides it towards the goal, exploring fewer unnecessary states. But, designing good, admissible, consistent heuristics, that's often the real art and challenge in applying A. The better the heuristic, the better A performs.
Fascinating stuff. Okay, let's shift gears a bit. What happens when the AI isn't just solving a static puzzle, but playing against, well, an opponent? Someone actively trying to mess things up for it, like in chess or tic-tac-toe. This feels like a whole different ballgame.
It is. This is adversarial search. You're searching in a space where an opponent has opposing goals. For deterministic, two-player, zero-sum games, where one player's win is the other's loss, the foundational algorithm is minimax. Minimax assumes your opponent will also play optimally to minimize your score, while you play optimally to maximize it.
Okay, how does the AI even represent a game like that?
Similar building blocks, actually. You need an initial state, the empty board. A player function tells you whose turn it is, the possible actions or moves from the current state. A transition model shows the board state after a move. A terminal test checks if the game is over, win, lose, draw. And crucially, a utility function assigns a score to those terminal states. For tic-tac-toe, maybe +1 if X wins, -1 if O wins, 0 for a tie.
Right. Max wants +1, min wants Michael 1.
Exactly. So the max player, say X, looks ahead. For every possible move, it assumes the min player O will make the move that leads to the lowest possible score for Max. Knowing this, Max chooses the initial move that leads to the state with the highest score after considering min's optimal countermove. It's this recursive back-and-forth reasoning.
Like looking down the tree of possibilities. If I go here, they'll go there, then I'd go here.
Precisely. It explores the game tree, calculating the value of each node by recursively looking at the values of the nodes below it, all the way down to the terminal states where the utility function gives a direct score. If you can explore the entire game tree, Minimax guarantees finding the optimal move for the current player, assuming the opponent also plays optimally.
That sounds computationally intense, like really intense. Tic-tac-toe, okay, maybe doable.
Yeah.
About 255,000 games, you said. But chess, wasn't it something like 10 to the power of 29,000 possible games? You can't explore that entire tree.
Absolutely not. It's completely intractable for complex games. Full minimax is impossible, and that's where optimizations become absolutely essential. The most famous one is alpha-beta pruning.
Alpha-beta pruning, what does that do?
It's a clever way to cut off entire branches of the game tree without even exploring them. Basically, during the search, if the algorithm realizes that a particular branch cannot possibly lead to a better outcome than a move it has already found elsewhere, it just stops exploring that branch. It prunes it. It's like saying, okay, I already know I can guarantee getting a score of 5 down this other path, this current path I'm exploring. The best my opponent can force me down is a score of 3, no point exploring it further. It saves a huge amount of computation.
Ah, smart. Don't waste time on paths you already know are worse.
Exactly. But even with alpha-beta pruning, games like chess or Go are still too vast. So the next step is depth-limited minimax. You simply don't search all the way to the end of the game. You set a depth limit, say, search 10 moves ahead or 12 moves ahead.
But if you stop early, how do you know if the position is good or bad? It's not a win or loss yet.
Right. That's where the evaluation function comes in. When the search hits its depth limit, instead of a utility function, which only works on terminal states, you use an evaluation function to estimate the value of that board position. This function looks at features of the game like material advantage, piece mobility, king safety in chess, and assigns a score. It's the AI's best guess about how good the position is. The quality of this evaluation function is absolutely critical to how well a depth-limited AI plays.
Wow. So it's a combination of searching as deep as feasible, pruning intelligently, and having a good way to judge positions mid-game.
That's the essence of modern game-playing AI, yes.
Okay, so we've covered navigating mazes, finding routes, playing games. These algorithms sound powerful, but maybe a bit abstract. How does this connect to, the real world, especially something like cloud computing, which you mentioned?
Oh, these concepts are everywhere in cloud infrastructure, often behind the scenes. Think about resource allocation. You need to deploy a new application. Where should it go? Which server? Which virtual machine? An AI can model this as a search problem. The state is a potential allocation, the actions are assigning resources, and the cost might be latency, CPU usage, or actual dollar cost. Algorithms like A or variations can search for the optimal allocation state that minimizes cost or maximizes performance.
Okay, finding the best spot for your app. Makes sense. What else?
Network routing. How does data get from point A to point B efficiently across the cloud network? That's a classic pathfinding problem, just like finding driving directions. AI search algorithms figure out the best path for data packets, minimizing latency or the number of network hops.
Like ways for data packets.
Pretty much. And load balancing. When tons of traffic hits a service, how do you distribute it across multiple servers so none get overloaded? That's an optimization problem again. The AI searches for the best distribution strategy, the state, by taking actions, directing traffic, to minimize response times or balance the load.
And what about when things go wrong?
Automated fault diagnosis. Complex cloud systems generate massive amounts of logs and metrics. When there's a problem, AI can use search techniques to sift through this data. The states might be patterns in the logs. The goal is identifying the root cause of the fault. It's searching for the needle in the haystack.
And I guess games hosted in the cloud, the AI opponents are using Minimax.
Absolutely. Especially for complex strategy games, they'd be running minimax-like algorithms, definitely with alpha-beta pruning, depth limits, and sophisticated evaluation functions to challenge human players.
It's really quite amazing how these core ideas, states, actions, costs, searching systematically pop up in so many different areas. We've really journeyed from simple maze solving to complex game strategy and even managing huge cloud systems.
We have. It shows how AI takes these complex, sometimes messy problems, gives them structure, formalizes them, and then applies these powerful systematic search methods to find solutions. And of course, the next layer is machine learning, where AI can learn better heuristics or evaluation functions from data, improving its search over time. But these fundamental search principles, they're right at the core.
So here's something to think about. We've seen AI use these search techniques to tackle everything from mazes to chess to network optimization. What other big, complex human challenges, maybe in science, city planning, maybe even art or creativity, could we potentially reframe as a search problem? What if we could define the states, the actions, the goals, the costs? Could AI then help us navigate towards solutions we haven't even considered? What stands out to you about applying this problem-solving mindset beyond just computers?